In this section, we are going to study an example of superposition of waves and the same frequency traveling in opposite directions. Imagine a string stretched between two fixed points. If the string is pulled at the middle and released, we get what is known as a stationary wave. Releasing of string produces two progressive waves traveling in opposite directions. These waves are reflected at the fixed ends. The waves produced in the string initially and the reflected waves combine to produce stationary waves. In these two figures, you can see the first figure, which is diagrammatically representation of stationary waves, and second figure shows stationary waves practically. In these two diagrams, you can see maximum displacement points, which are known as antinodes, and minimum displacement points, which are known as node points. Now let us study how to derive an equation of stationary wave on a stretched string. Consider two simple equal amplitudes small a and wavelength lambda form string in opposite directions. You know that 2 pi by lambda is equal to k and 2 pi n is equal to omega. The equation of wave traveling along the x-axis in the positive direction is given as y1 is equal to a sine of 2 pi in the bracket nt minus x upon lambda. The equation of wave traveling along the x-axis in the negative direction is given as y2 is equal to a sine of 2 pi in the bracket nt plus x upon lambda. By using superposition principle, we get the displacement as y is equal to y1 plus y2. Therefore, in the next step we can write y is equal to a sine of 2 pi in the bracket nt minus x upon lambda plus a sine of 2 pi in the bracket nt plus x upon lambda. Now we are going to use the identity sin c plus sin d is equal to 2 sine of c plus d upon 2 cos c minus d upon 2. In this case, c is nothing but 2 pi into nt minus x upon lambda and d is equal to 2 pi into nt plus x upon lambda. By using this equation, we get the displacement as y is equal to 2a sine of 2 pi nt cos of 2 pi x upon lambda. That can also be written as y is equal to 2a cos of 2 pi x upon lambda sine of 2 pi nt. Now here we can substitute for 2a cos 2 pi x upon lambda as capital A. Then the above equation becomes y is equal to capital A sine of 2 pi nt. We can also write this equation as y is equal to a sine of omega t, because omega is equal to 2 pi n. Now the final equation y is equal to a sine of 2 pi nt is nothing but equation of a stationary wave which gives resultant displacement due to two simple harmonic progressive waves. Condition for node points. Nodes are the points of minimum displacement. This is possible if the amplitude is 0. That means 2a cos of 2 pi x upon lambda should be equal to 0. In the next step, we can write cos of 2 pi x upon lambda is equal to 0. Now we have to understand which angle of cos is 0. In the next step, we can write 2 pi x upon lambda is equal to pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2 and so on. After solving this for x, we get various values as x is equal to lambda upon 4, 3 lambda upon 4, 5 lambda upon 4, 7 lambda upon 4 and so on. In general, we can write x is equal to, in the bracket, 2p minus 1, bracket complete, lambda upon 4 of lambda upon 4, where p takes the values of 1, 2, 3, 4, 5 and so on. The distance between two successive nodes is lambda. You can consider any 2 points which are 3 lambda upon 4 and lambda upon 4, suppose. The difference between these 2 points is nothing but lambda upon 2. If you consider second example, for x is equal to 5 lambda upon 4 and 3 lambda upon 4, then again the difference between these two successive points will give you lambda upon 2. This verifies that the distance between two successive node points is lambda upon 2. Now moving to the condition for antinode points. Antinode are the points of maximum displacement. That means amplitude capital A should be equal to plus minus twice A. That is 2a cos of 2 pi x upon lambda is equal to plus minus twice A. In the next step, we can write cos of 2 pi x upon lambda is equal to plus minus 1. Now here we have to think cos of which value will give you 1. In the next step, we can write 2 pi x upon lambda is equal to 0, pi, 3 pi, 4 pi and so on. After solving this equation for antinode point, we get x is equal to 0, lambda upon 2, lambda, 3 lambda upon 2 and so on. In general, we can write x is equal to p lambda upon 2. That means integral multiple of lambda upon 2, where p takes the values as 0, 1, 2, 3, 4 and so on. The distance between two successive antinodes is also lambda upon 2. Let us see one example. You can consider any two successive antinode points, that is lambda upon 2 and 0. If we take the difference between these two, it comes out to be lambda upon 2. Let us consider next example. The two antinode points are 3 lambda upon 2 and lambda. If we take the difference between these two, we get again lambda upon 2, which verifies that the distance between two successive antinodes is lambda upon 2. Nodes and antinodes are formed alternately. Therefore, the distance between a node and an adjacent antinode is lambda upon 4.